All right, tell your mom you need an extra big bowl of ice cream, settle down, and let's look at percent dissociation. So percent dissociation is just another way of referring to weak acids and how they ionize. So with a weak acid or a weak base, when we look at the percent ionization, like we have in this one, so the percent ionization is 0.767%. That means 0.767% of our acetic acid, the HC2H3O2, is dissociating. So when it breaks apart, 0.767% of it will be the ions. So if we wanted to take a look at this question right here, and we do want to take a look at this question right here, we would start off then by drawing in the equation just so we can set ourselves up an ice table. And notice how on this acid, with a lot of the organic acids, we keep the hydrogen separate. So we've got an H there, and then we've got three other H's there. We don't write C2H4O2 because we want to keep this hydrogen separate, and that's because that's the hydrogen that breaks off and forms those protons in the solution. These three right here are untouchable. They're covalently bonded to the carbons and the hydrogen, so they do not move. We keep them separate then just so we know that there's only one hydrogen that ionizes as opposed to four. And if we set up our ice table in this case, so we started off with 0.300 molar of the solution. That means that is the starting concentration. Let me get a different color. Of our acetic acid, and we would start with 0 of those because nothing is ionized yet. The acetic acid is going to decrease by X. The protons and the acetate will both increase by X. And so then at equilibrium, this is 0.300 minus X, and H plus is plus X, and acetate is plus X. So we need to do two things in this question. We need to find the pH, and we need to find the Ka. So to find the Ka, we would plug these values into the Ka equation. Obviously there's no numbers, but I'll show you how to get those numbers. Let's remember those, go to a clean screen then. So Ka is going to be equal to, in this case, the concentration of H plus times the concentration of the acetate, which is C2H3O2 minus, divided by the unionized acetic acid, so HC2H3O2. And we know that at equilibrium, it's going to be X times X divided by 0.300 minus X. And since we don't know the value of the Ka as of right now, we can't make the approximation and leave this minus X off. Because remember, you'd subtract this value from the 0.300 to see if that minus X was valuable. Since we don't know what Ka is, we can't make that approximation. So let's leave it in there for now. So to figure out the value of X, since we know at equilibrium that the original acid, the acetic acid, dissociates by a 0.767%, that means that X would be equal to 0.300, so that's the original molarity of the acetic acid, times 0.00767, which is just 0.767%. So if 0.767% of 0.300 ionizes, that means X would be equal to essentially 0.767% of the original. And so that means our X value is going to be 2.30 times 10 to the negative third, and that would be molarity. That's 2.30 times 10 to the negative third, if you can't read that. So now we can take this value then, since that's our X, and we can plug it in for those X's in all three places. And we don't need to use the approximation rule because we've got our X right there, so why bother? And when we do that then, it would be Ka equals 2.30 times 10 to the negative third, and we'll just say that's squared since both of those X's are the same value, divided by 0.300 minus 2.30 times 10 to the negative third, and that will give us our Ka as 1.78 times 10 to the negative fifth. So that would be our Ka value for acetic acid at whatever temperature this is. And then the next part of the question asks us to find the pH, and the pH uses the negative log of the H plus concentration, so it would be that value right there. And since that value was our x value, finding this would just be taking the negative log of this 2.3 times 10 to the negative third value. So if we negative log 2.3 times 10 to the negative third, that would equal for us 2.64. That'd be it with sig figs. This is 2.30 right there, so it'd be 2.640 as our answer for our pH. So remember what we talked about today in class, that the pH calculation, since they use that log, the only thing that counts as sig figs are the numbers after the decimal. So our original number, 2.30, 3 significant figures. This answer right here has 3 significant figures. That 2 right there does not count. So that's how you would calculate the pH and the Ka from percent dissociation.